Yeah, I think now we are recording. So in the last class, we were discussing about the capacitor, why it is important, how it is helped in the as a filter circuit in the filter circuits. So inductor also comes do some similar things. For example, inductor we usually represent by the symbol, and if the inductor are connected in series, so the L equivalent will be L1 plus L2. This one is L1 and this one is L2. And if our inductors are in parallel, for example, like this, it is L1, it is L2, it is L3, then L equivalent will be 1 by L1 plus 1 by L2 plus 1 by L3. It is something similar to the resistors. Okay. So the for common formula for inductors are it is V equal to L into di by dt. And for the capacitor, remember it is for the capacitor it is something like I equal to C into dV by dt. So if you look at this equation, what you can understand, like when the current is does not vary with the time, then di by dt will be 0 if current does not vary with the time. That means that inductor will act like a short circuit. So when as I said, di by dt is 0, V equals 0, and hence inductor will act like a short circuit. If you remember, it is little different in the case of capacitor. For capacitor, as I said, this is the equation. When it is for steady state, the current will be 0 for capacitor. That implies that it actually is an open circuit, right? Like an open circuit. Okay. So the thing that you have to keep in mind is that the current does not I mean the current through the inductor can change instantaneously. Current through inductor can change instantaneously. And for example, in the capacitor, the voltage across capacitor is also can change instantaneously. So that's the idea. For inductor, the current you cannot change instantaneously. For the capacitor, the voltage you cannot change instantaneously. And yeah, I think that's about capacitor inductor. And let's look into let's before going back to our circuit analysis tools, the Thevenin or Norton or other mesh analysis or something. We'll just look into the current and voltage division rules. Not rules, current and the voltage divider we usually do. For example, if you have some circuits, if you have some circuit like this, which is resistor R1, this is R2, and this is R3. So the rule is, if you want to find a voltage drop on V1 or V2 or V3, or in general Vn, sorry, in general Vn. In general Vn, if you want to find out, the Vn will be the total or the source voltage Vs divided by sum of resistances sigma Ri into the resistance. For example, if you want to find V1, it will be Vs divided by R1 plus R2 plus R3 into R1. Okay, so this is a voltage division rule. This is a general equation. And for example, if you have a current, in the case of current, if you have a current circuit, this one like this, R1, R2, R3. So this is a source current. So this is be like, it will go like I1, it will be I2, it will go like I3. So if you want to find out any current, then current will be almost similar to this equation. But the thing is, the resistance will be inverted. For example, if you are finding IN as generalized case, then IS divided by, instead of sigma Ri, it will be sigma 1 by Ri, and into, instead of Rn as in the voltage divider, it will be 1 by Rn. That is, for example, if you want to find I1, it will be IS divided by 1 by R1 plus 1 by R2 plus 1 by R3 into 1 by R1, right? So this is the equation for current, and this is the equation for voltage. These are the voltage divider and current divider circuits, or the basic rules. Okay. So now I think you understand how a capacitor inductor is important, and we are looking into voltage and this one divider. Now let's look back to then our circuit analysis tools. As I mentioned yesterday or in the previous classes, there are a few circuit analysis tools. One is nodal analysis, another one is mesh analysis, and Thevenin, Norton, all that kind of stuff. So nodal for the which one we will take, which we will first look into nodal analysis. So generally people say the nodal analysis and mesh analysis are basically a brute force method. Brute force method means they don't give you insights. You can just like a mathematical problem or something, you can just solve it, but it won't give you some insights. And nodal analysis, what exactly we do, for example, if I have a circuit something like this, I just took a R1, then R2, then R3, R4, R5. Okay, so okay, so my pen is not working. Yeah, now it is working. Okay, so what we do in nodal analysis that we will, the variable in nodal analysis are node voltages. Okay, I think you know like what node is like, right? If it is a point where 2 or 3 circuit elements join, for example, this is a node. Okay, so variable will be node voltages. But if you are looking in the mesh analysis, it is current. Here in nodal analysis, it is node voltages. So what we do is like each node, we will just look at what are the node voltages. With respect to a pre-selected reference node, we will take one node as base like 0. Then compared to that, we will do the other voltages. The reference node we actually also called as ground. Okay. So for example, we have, if you look here, here I will just redraw it. Okay. Okay. So if you look here is a voltage source. Okay. This is a node. I will call it as 1. This is a node. We can call it as 2. This is a node. We can call it as 3. So what we do is we will apply the Kirchhoff current law in each nodes, and from there we will get the value. For this node, I will just take it as ground. Okay, so that's the thing. Nodal analysis will take one as base, or the ground, and compared to that, we will find out all the other voltages. So if you apply the KCL at node 2, node 2 means the center node. You can see, right? See, the current at this point will be, it is a voltage at V2, or the logic is like this. If the current is, since the source is here, the current will come like this. So the voltage at V1 will be higher and voltage at V2 is low. That's why current is flowing from 1 to 2. So this will be V1 minus V2 divided by the resistance. It is R2. Should be equal to what? Here we have this current will be going this way and this way, right? So the current and going in downside, it will be what? v2 minus 0 because we took it as a 0. This one is we took it as 0. v2 minus 0 by r3, or yeah, I would just write this r3 and r4 or anything. I mean the resistance in the middle. Okay, r3 plus no r4. Oh, yeah, sorry, it's my mistake. Okay, sorry. So v2 minus 0 by r4 plus here voltage is higher here, current is flowing in this direction, right? So v2 is higher, so v2 minus v3 by here r3. And the same way we can apply the KCL at node 3 also. If you take here, the current is coming from this side, current is coming from this side, current is going this side, right? So it is like we can take it as v2 minus v3 by r3 plus v1 minus v3 by r1 should be equal to v3 minus 0 by r5, right? Yeah. So we know these are the two equations, and hence since it is considered, it will v1 should be equal to v3, and from if we solve all these three equations, so if we solve all these three equations, we should get the whatever the value v1, v2 and v3. So that's how nodal analysis work. The basic idea is we are using the node voltages as a parameter, and from that we'll take one as a one node voltage as base, and from there we'll write the KCL and KVL. So if you see, the KCL and KVL are the basic bloodlines of electronics circuits. If you know that one clearly, like we can somehow solve a problem. Okay. Anyway, okay. So we have looked in nodal analysis. So let's have a look at mesh, right? Mesh analysis. Okay. So in mesh analysis, there is a simple thing. In mesh analysis, we are using the current as variable. The previous node analysis we are using voltage, right? Here using current as variable, and here we'll apply the KVL. When current is variable, we are applying KVL, and the previous one node analysis voltage was variable, then we are applying KCL. Yeah, you got it right. Okay. So mesh analysis, for example, if I just draw the same circuit which we drew in last time. So it's like take R1, I'll take R2, I'll take R3, R5, R4. Okay, this is the same circuit. So in mesh analysis, as the name indicates, there's a mesh. Mesh means mesh will be is same as a loop that we are discussing. Mesh is same as a loop where there is no other loop inside of that. Okay, so for example, this is a loop, this is a loop, this is a loop. I just name the current as I2, I3, and then here I1. Okay. So let's apply the KVL here in each loop. For example, if you take the mesh 1, which is this one, so in the mesh 1 you can see we had to apply the voltage, right? So here initially the current is I1 is going in this direction, so I1 into R1. So I1 into R1 plus, if you see like this, when it comes like this and this way, you can see that in the opposite direction I3 is coming, right? As you can see in the indicator. So this and this will be minus, so we will have I1 minus I3 into the resistance R3. Okay, R3 plus, if you when the current reaches here, you can see I2 is coming in this direction, so it will be in opposite. So I1 minus I2 into R2. So sum should be 0. And if you look at the mesh 2, sorry for my bad handwriting. Okay. Okay, if you look at the mesh 2, we are, as I said, here we are going from negative to positive, so it is minus Vs plus. Here if you go this direction, I2 is coming from I1 is in the opposite direction, right? So I2 minus I1 into R2 plus, then at the end we will have I2 minus I3 into R4 equal to 0. So in a similar way, if you look at it, it will be like mesh 3. If you take it will be I3 into R5 plus I3 minus I2 into R4 plus I3 minus I1 into R3 equal to 0. So now you got all the three equations. From that you can calculate whatever you want. So there is a mesh analysis. So now all the algebraic, I mean the mathematical, just rearrange, substitute, and that kind of stuff, right? So the thing about this Nodal mesh analysis, they are actually we call a brute force method. They are just, I mean, they are just applying KVL and KCL by considering the current and voltage as parameters, and we are doing it. But it don't give any kind of insights. But if you are taking the case of other methods, it will give you some insights. There are one method called as reuse method, where we will be using the what are the equation we have learned, and we'll build upon that. From there, like what we will be writing, like for example, if you have resistors like this R1 and R2, in that method, when we write, we won't take the 1 by R equal to 1 by R1 plus 1 by R2. We directly write in the equation itself, like for example, R1 is parallel to R2. So in the equation itself, we will writing like this. So we can see, okay, this is parallel and this is parallel. So if we change it like this, it will happen. So that kind of that feeling will come, that insight we will get. So that's the reuse method. That is not that important. And then we'll have Thevenin and Norton, which are actually important if you look at the previous year gate, or I mean for electronics or physics. Usually it comes. In the past it was used to come a lot, but nowadays I can't see much, but still it is important. If one question came from this area, you should not miss it. That's the thing. Okay. So then Thevenin and Norton actually, these are, if you have a circuit, if you have some kind of circuit, we'll be making, if you have some circuit, some complex circuit, you have some there are a lot of resistor, capacitor, and voltage sources, and everything is connected. Some kind of circuit you have. So what you do is using the Thevenin, if it is like this, okay, if you have a resistance here, so if we'll write the equivalent circuit. For example, if it is a Thevenin, we will have, but we will write this entire this circuit as a equivalent circuit of, like, with a voltage source, which we call as V Thevenin, and and the resistor connected to R Thevenin, and this is our circuit. This is a 1 amp. Okay. So the entire this big circuit we will be writing as a V Thevenin and R Thevenin, like equivalent one. That is the Thevenin theorem, or Thevenin equivalent circuit method. For if you are looking for the Norton, what they do is this entire circuit I told, right? So they will be making it as a, instead of a voltage and resistance, they will be making it as a current source and parallel resistance. See, like this they will make, or not they will make it. It is how it work. Okay. So now we made as an entire current and resistance equivalent circuit. So the basic idea of Thevenin and Norton is that if you see a circuit, for example, any circuit, in a Thevenin and Norton, what they do is actually they are reducing the number of, if you look at it carefully, we are reducing the number of mesh. For example, if let's take a circuit, for example, I have a voltage source, I have some resistor, like this, R1, R2, then we have R3, then we have R4, another voltage source V2, then R5. Is enough? Should I? Okay, this is enough. R6, we have V output. Okay. So in the Thevenin, what they do is they will simplify. For example, if you want to simplify this area, if you want to make it a simple, then what we need a, as I said, we need a Thevenin voltage and we need a Thevenin resistance. Thevenin voltage and Thevenin resistance. So for that we will be rewriting this this circuit, this big circuit, for finding the resistance, for finding the R Thevenin. What we'll do, we will just remove all the voltage sources. So what we will be writing like this: R1 is here, and we will remove the V1 we had here. We have V1, right? So we'll remove that, and we have R2, then we have R3, then we have R4, then okay. So this equivalent circuit we will do, and we'll get the Thevenin. If you see, this is this is only one mesh. Like this R1 and R2 are parallel, so you can make it a one. So it's a one mesh, right? So this big circuit was actually a three mesh problem. But here now it is a one mesh, and for finding the voltage, if you see, what we do is, we will at the end we will make it open circuit. I mean, this part, no, this part, this will make it as an open circuit. So I will just draw the circuit for that also. It is okay to sleep in my class, and you can pause it and go and watch it again, because it's all are in YouTube and it's online. So I mean, electronics, I understand that electronic stuff is a little boring for some people, and some exceptional human beings it is very exciting. So, and it depends on my class also. My class is also not that great, and I know that. So it's okay to rewind again and go and come back. Maybe pause the video and go and come back. Okay. So as I said, we will be this area we will be open circuited. We open circuit. Now we can see this is also two mesh problem, right? So this was a three mesh problem. This will be one mesh. Then this is a two mesh. So what basically happens is, when you apply Thevenin or Norton or anything, yeah, if we have a n complex n circuit, or n mesh circuit or something like that. So if you apply Thevenin or Norton or anything, it will become n minus one complex. For example, n will be n minus one. Then if you again Thevenin and it is n minus two, then again n minus three, like that it will go then one it will reach. Okay. I means only one mesh means only not one. There will be lot of circuit with only one complexity. Understand? Okay. So that's how it works. For the Northern also it's the same case. So let's try an example. Let's solve a problem, a simple problem that will give you an insight of what is Thevenin and Norton actually means. Okay. For example, let's take a simple circuit. This is a simple circuit we have. We will call A, B, and we have a 50 volt this thing here. Okay, we have 50 volt voltage source. So if I want to use the Thevenin and this one here, what I will do, so the idea is we have to write this entire part as a button. I mean this as this is. Okay, so if I want to find R Thevenin, what I will do now, I will remove this voltage source. So what will happen is this will be 5 ohm. Okay, it will be 5 ohm. It is very easy to draw the resistance, right? Like this. Okay, 5 ohm, and this will be 20 ohm. These are parallel, so you know how to do it. Parallel, and this is 4 ohm. Okay. So and there when you did parallel plus this will come around. So orthogonal will come around 8 ohm. Okay, 8 ohm it will come. So and when you want to find the voltage, you can see right in the circuit. If you look at, you can see that you have it is open circuit. So here I will just redraw it, or I will just clean this. Okay, here the current, if you write the Ix, the current Ix is 0, right? Because the other end AB is open circuit, so no current is flowing. So you can actually basically remove 4 ohm, because no current will flow. So you can just remove the 4 ohm, and if you write like this, then we can just redraw it, which will be like 50 volt, 5 ohm, 20 ohm. VAB. It is AB, VAB. Okay. So now how we will find VAB? You know, I told you the voltage divider, right? So if you want to find a VAB, what you will do? We will multiply with the source voltage 50, and VAB is the voltage across this resistor, right? So the R or Vn is equal to Vs into Rn by R1 plus R2 plus R3 plus like that. So Rn 20 divided by 20 plus 5. It will come around 40 volts. So that is our Thevenin. So this circuit, this big circuit, you can write it as 40 volt voltage source and an 8 ohm resistor. These both are equivalent. These both are equivalent. This and this. Okay. So it is simplified. So this entire complex circuit you write it as a 40 voltage source and resistor. The same way you can do the Norton also. Or one thing you can do is now you have got the Thevenin circuit, right? You can directly convert to Norton circuit. For Norton we need a current source and we need a resistor like this, right? So here you can see it is 40 volt and it is 8 ohm. So current is, you know, V get IR and V by 40 by 8, it will come around 5 ampere current, and the resistor is same 8 ohm. So this is a Norton circuit. You can interchange Norton and this one you can interchange. So I think now you get an idea about Norton, equivalent, Thevenin, Norton, Thevenin, mesh analysis, nodal analysis, and everything. And for the problems and everything, maybe I can put a few PPTs which will be helpful for your reference as a link in the comments or in the video section, description section. Just look into it and let me know the section how is the video in the comments, or you can directly message me also. If you just search in LinkedIn, you'll get my name. You can just search Muhammad Sajid. The spelling is like MUHAMMAD. Yeah. Okay, Muhammad Sajid. Okay. So that's it. That is about today. I think we will see you in the next class. I just stop recording. Just cut.